Thank you. I'm here today to talk to you about our accelerometer system, which we designed for the DARPA N0 project. And I'm part of our DARPA N0 team at Sandia National Labs. So I'll start the talk today by giving you a little bit of background about what DARPA N0 is and what's the purpose of it. And then I'll move on to talk about our particular part of the project, which is titled the Aluminum Nitride Resonant Integrated Sensor, or RISE. We'll then move on to talk about the accelerometer that we designed, and then the CMOS ASIC, which we designed to go with it. And then we'll talk about them together as a system and their system level performance. And we'll move on to give a summary and some of the stuff we're working on for future work. So DARPA, and this figure should look familiar to everybody, but DARPA has identified a need for networks of sensors that are continuously aware, but they're aware for kind of infrequent events. And commercial off-the-shelf sensors for this application require just too much power because the battery replacement cycles go on the order of weeks or months versus what we're looking for, which is on the order of years. So our approach to solving this problem was to use piezoelectric MEMS along with very low power CMOS to get a solution to this problem. So we use piezoelectric materials for the problem because they require zero input electrical power and they give you an electrical output signal. We chose aluminum nitride as our piezoelectric in this case, and we integrated them with very low power sub-threshold operated CMOS. We then combined these two systems to create a single channel wake-up system that takes only 5 nanowatts of power both before and after the wake-up event occurs. So our technical approach to this is that we have some physical signal shown here in the environment, and we're trying to select a target frequency from this spectrum. We then design a passive piezoelectric frequency selective accelerometer, which selects that frequency that we've chosen from the physical signal and basically does a zero power signal filtering in the mechanical domain. It's a second order oscillator basically. We then pass the signal through our accelerometer to get the accelerometer output signal shown in the bottom right, where we can now see that the target frequency that we selected at the beginning is amplified compared to everything else in the spectrum. We pass that through our 5 nanowatt, 0.35 micron CMOS comparator and latch system, and we get as an output a 1 volt wake-up signal. Now we understand a little bit about how the overall system is going to work together. We'll focus first on the accelerometer portion of it. So our accelerometer is shown here in a top-down view and then also from a cross-section in the bottom right. The accelerometer is formed by a full thickness silicon wafer, and we have these tethers. I don't see the laser pointer, but we have the tethers. I thought you'd get away with it. We have the 4 tethers in each of the corners, and they act as flexures, and they're created from, So the flexures are created from single silicon or single crystal silicon, and they have an aluminum nitride layer incorporated as the top. And in the middle here, we have a tungsten mass, and we chose to use tungsten instead of silicon in this case because it makes it replaceable, which means that we can change the frequency, the resonant frequency of the device after it comes out of the fabrication process. And it also provides additional density compared to silicon, so it gives us the ability to go to lower resonant frequencies and also to get higher peak resonant response sensitivity. So I'm showing here the finite element analysis results. What I really want to focus on is these flexures that I talked about in the previous slide. where the flexures around the edges act like springs and deform when exposed to an acceleration. The deformation in the flexures causes a stress in the aluminum nitride, which creates an open circuit output voltage, and we pattern the electrodes here such that we are maximizing the output from the devices by focusing only on one aspect of the stress. So in this bottom left corner, we would place the electrodes only over the blue or the red portion of the stress field, but not both. So some of the things that we've demonstrated from these accelerometers is that we've matched the resonant frequency targets to within 0.1%. We've seen quality factors of up to 12,500, and we've had open circuit sensitivities of up to 450 volts per G, as well as resonant frequencies as low as 43 hertz. So in the bottom left-hand corner, we have a plot of the frequency response function of one of these devices where we're showing the open circuit sensitivity versus the frequency. And you can see that this device is operating at 97 hertz and we're getting 452 volts per G out of the device. On the right, we have an example output versus the input. So we're showing here the MEMS accelerometer output in blue, as well as the reference accelerometer, which we're using to compare to in the red. And we see that while we have very low output from the reference accelerometer, we're amplifying this single frequency out of that spectrum and getting a time series that basically looks like a sine wave. So now that we've talked a little bit about the accelerometer and its performance, we'll move on to talking about the ASIC. So Sandia's CMOS process is coined CMOS 7. It's a 0.3 micron silicon and insulator trench isolated process. And what we think is the most important thing out of this is that that our process at Sandia is trench isolated, which we think is providing us the ability to get to much lower power because we're isolating these the silicon from itself using an oxide, and we're therefore lowering the leakage into the substrate. So some of the results that we've seen from just the ASIC itself is that we successfully tested the comparator chip with the function generator input, and that result is shown in this bottom right corner. At the top, we have the function generator input to the comparator, and then in the middle, we have the comparator output, and at the bottom, we have the latch output. So basically, we can see that whenever the function generator goes above a certain threshold level, we get a comparator output of here shown 1.5 volts, and then it goes back down when we go below that threshold. However, the latch system says that as soon as the comparator goes high, it just latches and holds at the 1 volt, or the 1.5 volts in this case. And we then have an electrical reset on the back end of that. And so we do this using long channel FETs with sub-threshold biasing, and we consume only 5 nanowatts of power both before and after the wake-up event. So that's when we're having 0 latch output as well as the 1.5 volt latch output. So now we'll talk about them together as a system. So the accelerometer we tested is shown here, and I'll walk you through this figure. So in the blue, in the back, we have what's going to be our target signature, which in this case is a generator. And we also show in the back the all quiet data, or just the background noise. So what we're trying to do with this accelerometer is to match one of these large peaks in the blue acceleration spectrum with the accelerometer resonant frequency, and then in the red, we're showing the device sensitivity. And we show how that we match this 160 hertz peak very well. So this is the typical output of one of our systems. On the left, we have the response to a generator being on, where we see that we get an output voltage versus time, and each of these individual pulses is a wake-up event. So basically, as soon as we turn on the generator signal, which basically we have our accelerometer system is on a shaker with a reference accelerometer, and as soon as we turn the shaker on with this generator input, we're getting immediate wake-up events. And these constant blocks of data are just like, is when the device is constantly waking up. We then played back the all quiet or the background noise data, and we show that versus the 90 seconds of time for this data file, we don't have any false alarms. And we've tested this for hours per the DARPA project, and it hasn't had any false alarm wake-ups to this background noise. So looking at this a little bit more in depth, and I'll walk you through this figure. So what we're showing here is each point on this graph is a certain threshold setting for our comparator. So the point that we choose as an example here is 100 millivolt threshold. And then on the y-axis, we have what's called the fraction, what we call the fraction of the generator on data. And essentially that's just what the percentage of the total generator amplitude that we're applying. So if you had a generator sitting here, it would be giving you 100%, but our shaker couldn't handle that much shaking. So we had to go lower than that. And so in this example, at 100 millivolts threshold, we got about 6% of the generator input was enough to trigger the wake-up event, which we're looking for. In the same vein, on the x-axis, we have the amplification of the quiet data. And we're showing here that for this point, we have about 180% of what the quiet data was to trigger a false alarm. And so this is basically showing the margin of our devices, so 6% of the generator versus 180% of the background noise. And even at the highest points, we're at about 8% with 240% of the background noise. So in terms of future work, we're currently working on doing a multi-channel wake-up where we take a single CMOS chip and we connect it to two, in this case two, but possibly 4 or 8 or 16 different MEMS devices in order to increase the robustness. So you could imagine a circumstance where you have a plane flying over, for example, and it generates this frequency. And we want to be able to get rid of that false alarm potential. So if we select a second frequency or a third or fourth, then we're much more robust to those background noise wake-ups. And we've tested this a little bit, and we've shown that it operates at about 6 to 7 nanowatts for the 2-channel system. We're also looking at doing a very low power transimpedance amplifier. So if we wanted to, instead of lowering the threshold, we could potentially boost the signal coming in. And that consumes about 3 nanowatts of power. And then we're also looking at doing on-chip machine learning with state vector machines so that we can take more complex frequency signatures and analyze them on chip for example, this truck. With that, I'd like to thank DARPA for funding this project and open the floor to questions.